So in chapter 3, now there's our models which have more than one parameter, and then we come with discuss these terms, joint distribution, and how we can then focus on some parts of the joint distribution, so marginalization. I mostly use the normal distribution example, and then in the end I also explain more about the bioassay example, which is important as it's used in many of your exercises and also good example of generalized linear model. First, just the kind of the visualization of uncertainty in modeling. We have some observations. They are x values and y values, and we would like to know kind of the relation between x and y values. And we might think that maybe this is linear, and here we would have just the point estimate, what would be the best linear model fit to this data. But then, since we have finite number of observations, we can have also other possible linear models which could explain this data. And we can also compute predictive distribution given posterior mean, so we can predict what's the future, and we can do this also analytically. But you already did some sampling from distributions, but here today I also use a lot of these sampling ideas when I explain these joint distributions, factorization and marginalization. And you can see here there are a bunch of blue lines which could also explain this data. There are more of these blue lines close to red line, so they are kind of more likely. And then these are now based on computing the posterior distribution, getting samples of intercept and slope values, and with each sample we can draw a line, and it's one way to visualize then this uncertainty in our model. We can also then use these posterior draws and our model to compute then numerically predictive distribution, which now when we add the red line, which was the exact, we can see that also we can with these posterior draws get good results, even if we would not have analytical solution. Now I use this normal distribution as an example where we have the analytic solutions, but also the sampling things. But in the end, with the bioassay example, we don't anymore have analytical solution, and then it's easiest to go with these sampling-based approaches. Now in the previous figure we had these posterior draws, and we can now denote, we have there the superscript S in parentheses, indexing that we have many of those, and then S going from 1 to capital S, and then each of these draws, the theta would in this linear model case include then both the slope and intercept, and we can obtain these from the posterior distribution, and we can use them for visualization as in the previous figure. But we can also approximate expectations. This is the computations or estimation of expectations is the most computational thing we do in Bayesian inference. And then kind of all these predictions and thinking whether some effect is away from zero or if there's more girl babies and so on, all of them can be in the end given as a sum integral, some expectation. And in this case, for example, if we would want to know what is the expected value, posterior mean of theta, we just get these posterior draws from this posterior distribution and compute empirical mean. We come later in chapter 10 to more about this kind of what is the accuracy of this approximation. Now it's just that if you have big enough and in your exercises before chapter 10, you can just use, for example, 1,000 draws from the posterior to compute these different kind of expectations. When we have a multi-parameter model, we have a joint distribution, so we have several parameters. Joint posterior is then formed by having some observation model, which then as a function of these thetas is a likelihood. So likelihood which depends on more than one parameter and prior for these. But sometimes we are interested in looking at this just some part of the model, some parameter. And then we can integrate over that the uncertainty related to these other parameters. And then we call this marginal distribution. And again, we can also use this Monte Carlo approximation to estimate these marginal distributions so that we have draws just from the marginal of theta 2, or you can see soon that how in these multi-parameter cases we can also get from the benefit from the joint samples from joint distribution. Predictive distribution, I last time talked about also that, mentioned that the benefit of Bayesian approach is that we integrate over the uncertainty when making predictions, and reminding again that this is also a case of marginalization, so that we are not necessarily interested in these intercept and slope parameters directly, but we are interested in making predictions with the new x value, what kind of y values we might observe, and then we integrate over the uncertainty related to model parameters. Here's a Gaussian example. Data which has been also generated from Gaussian, and then we also fit now Gaussian normal distribution to this. In this lecture also there's kind of two different levels where I go that I use a lot of visualizations, so if you have difficulties with the equations, I hope these visualizations give you anyway some intuition of these different concepts. But then those who are interested in going in more deep, I also in this lecture use a lot of equations, and then I recommend, if you want to understand them better, make some of these exercises which are listed end of chapter 3, and I also mentioned the best ones in course GitHub. and some of them are very useful for kind of looking a bit more about how this normal distribution behaves. So here's the equation for the normal distribution. With the red, I'm now, so the y, so we have a model how the y, how the observations would be distributed if we know mu and sigma. And then we have mu. In this case, I put in the place of mu mu hat, which happens to be the point estimate from the posterior. And then the black density here, it's also conditional on sigma, and for drawing the specific distribution I used sigma hat, which was then posterior mean of standard deviation. But then we don't want to use just these point estimates. We know we have uncertainty about these mu and sigma. And now I first illustrate just that these are these different normal distributions which could explain this data. Each of these blue distribution, it has specific mu s, and each of them has specific sigma s, and when we have obtained many posterior draws, we can illustrate the uncertainty that we don't know which of these normal distributions produce this data. And of course there's infinite many possibilities, but even with just plotting finite number of these possibilities, you can see and kind of get the idea of the uncertainty. Instead of now plotting all these possible distributions, we could also just look at what is the uncertainty now about mu, and look the center point of each of these possible distributions. And now these vertical lines are representing then just the posterior draws of mu. And this now then shows posterior draws of these mu. So these vertical lines are now the values of mu, but then we have also uncertainty about sigma, and so we have different sigma values. And if we draw more, we see the shape even more clearly. And this is one way to visualize now the uncertainty we have about if the data would be generated by normal distribution, what is our uncertainty about the location, and what is our uncertainty about the width of that distribution. Now here I have the same, these posterior draws as the blue dots, but in addition I've also drawn now these equidensity contours. So it's in the same way as in a map, we have these contours describing how high some hill is, and so the highest point, highest density is there in the middle where the inside of the smallest circle, and then density gets lower and we get some idea of the shape. But you can see that we can infer kind of similar thing also from these posterior draws. In order to make this kind of equidistant contour, I had to evaluate the density in everywhere in grid to make these contours. So we can then look at how does it look, this analytic solution for this posterior distribution. We can start with this non-informative prior. I did last time discuss that we should prefer weakly informative or informative priors and proper priors. This is now uniform for mu, so clearly improper, and also then this sigma to -2 is not proper, but then we still get proper posterior distribution. And so we multiply here now with the prior, and then if we have several observations yi, and if we assume that they come independently from this normal distribution, we can multiply them as we know from the probability theory. But we can also now, so here inside of that product we have under the line square root of 2 pi and sigma. So we have 1 per sigma multiplied by itself n times, so we can move that outside of that product. And then you remembering how product of exponented things go, we can move that product inside of the exponent as a sum. And then this 1 per sigma multiplied by itself n times is now there the sigma minus n. Then we want to do something so that we can make it even easier when we have a normal data. And this is the usual what we also last week I mentioned the sufficient statistic, that we want to rearrange the terms so that it's enough that we summarize the data in this normal distribution case just with the two summaries. This is something that it's one of the exercises you can do, how to go through these steps, that we calculate this square thing and then add and subtract y bar, which is just the average of these observations, and rearrange the terms to these two new squares. And then in addition we also then go from this yi minus y bar squared, so that it's also used as one of the summary statistics. So now s squared has that part. Interesting thing is now here that why do we want to have it so that s squared has this 1 divided by n minus 1? Because then we need to put the n minus 1 back in the equation. And we'll come back to soon why this convention is used. But now we ended up in there that this normal distribution can be, that we don't need to store all yi values after we've calculated the average mean y bar and this sum of squares divided by n minus 1. This slide has now the derivation how we got these intermediate results. I will now skip it, but I'll have it in slides so that afterwards you can go through it. So you can try first, do it yourself, and then check the answer from here if you couldn't do it. Okay. We're back to joint posterior distribution, where we have also these samples. Uh, we have two possible marginals for this two-dimensional distribution. We can look at the marginal of mu. So what is our uncertainty about the location of that normal distribution, which could explain some data. So, and this marginal is obtained by integrating over sigma. And we have then marginal of sigma, which we can obtain by integrating over mu. And you can also think of these marginals, the kind of the what if we have all these posterior kind of projected or squeezed in some direction, and I have some visualization of that more. Again, bit of equations. So we have an analytic solution for this sigma squared, and it was beneficial that we first derived that form of the distribution where we can use the sufficient statistics. So this is directly now inside the integral. This is the part we derived before rearranging the terms. Now for the integrating over mu, we can first move all the parts which don't depend on mu outside of this integral. And so inside of the integral, we have now much less of these terms, what we need. For this integral, we can recognize that it actually looks quite similar to normal distribution. If you compare now the last black line of equation and the green, the gray, so the gray is the normal distribution, and it has to integrate to 1. And we can then recognize that the difference is that instead of just sigma, we have the n divided by so in the inside of the exponential, what we have in the gray one, we have 1 per 2 and sigma squared, and in the black one we have n divided by 2 sigma squared. And then we are missing that part in the front of the exponential. But from that we can then infer that this integral has to be then this square root of 2 pi sigma squared divided by n. We can then rearrange the terms and drop this term constant. So we use the proportionality here, so we can drop the square root of 2 pi, and then we combine these different sigmas, and then we just wrote slightly differently the also thing in the parentheses. And now this is then called inverse chi-squared distribution. And now the convention is that then here this inverse chi-squared distribution depends on this s squared, and that's why we define that s squared in that certain way, that we had that divided by n minus 1, so that there's only one parameter here, which for this sufficient statistic part. Yes? Mm-hmm. Very good question. And it's so that Often we don't need to know that constant, so that for example, when we are computing this expectation using Monte Carlo, it was enough that we had these posterior draws. There are algorithms which can get these posterior draws if we just know the density proportionally. And then after we have the posterior draws, we can then just take these empirical means, and we didn't need that. And that's most of the computations in this course is such that the algorithms, either we do at some point some self-normalization, or we don't need to do that normalization at all. We can now also compare. So in the chapter 2 there was this known mean case where sigma is as sigma squared. Want to remind that in here I did do the marginal posterior for sigma squared because it's easier than for sigma, but otherwise I prefer to just talk about sigma. So you need to be careful also that sigma squared is the variance and sigma is the standard deviation. Sigma squared is easier, for example, in this computation, but sigma is on the same scale as the original observations and mu, so it is easier to interpret. Here the difference now compared to known mean case, the sigma has there also inverse chi-squared distribution, but you can see there's a difference that when we go from known mean to unknown mean, the first parameter changes from n to n minus 1. And this parameter controls in inverse chi-square how thick the tail is. So when we have unknown mean, because of that additional uncertainty about the mean, when we integrate over it, it makes uncertainty about sigma squared kind of the more uncertain, and it has thicker tail, more probability further away. And also then we have a change how this sufficient statistic, the second parameter is computed, which is the location of this inverse chi-squared. You can see that that location parameter also now shifts. Instead of dividing by 1 per n, it's 1 per n minus 1, and it's again because we had uncertainty about the location mu, and when we integrated over it, it made the distribution more uncertain. Probability distribution. Yes. And when here again the visualization. So now this blue line in the marginal, it's not inverse chi-squared because I again use as an axis sigma, but we can get from inverse chi-square, we can compute this. So this is computed using inverse chi-squared function, and all the code for this is in the demos, and there's additional R file for this slide specifically so that you can check all the how these plots have been made and how these are computed. And so you can see that the marginal for sigma, first of all, this sigma has to be positive. The width of the normal distribution has to be positive, and it is skewed towards the larger values. So it has a longer tail on the larger values. Again, because it's constrained to be positive, it has to have tail that ends before 0. Now here, this also now illustrates then that, okay, we had the joint distribution, we were able to compute analytically the marginal, but we can also now factorize this joint distribution to marginal part and conditional part. So this is again just based on basic probability calculus. We have the marginal p sigma squared given y multiplied, then the conditional p mu given sigma squared and y. And you can see in the left hand plot now that the green is a bit dark, so maybe especially in the back row you don't see, but there's the dashed line Gaussian. So I picked one value of sigma and then made a black dashed straight line, and then on top of that I illustrated how the shape, the conditional density of mu is along that line. And now we can then compute the density in any mu sigma squared location. If we first take what is the density for the marginal of sigma squared at certain point, and then the conditional density of mu and multiply them. And then that way we could again compute the density everywhere in the joint. Reminding now that the marginal is then this inverse key squared, and then the black dashed line is now just one posterior draw from that marginal. And given that one sigma squared value, the conditional is the same as if we would know the sigma, so it's just a normal distribution with parameters mu bar, so the average of the data, and sigma squared divided by n. And so this was just as a reminder, basic normal distribution. And then we can draw from this conditional distribution. So this way we can draw from the joint distribution, first draw from the marginal, given that draw from the conditional. And then these together are the joint. And there's a red dot in the figure showing how we could obtain one posterior draw from the joint. Repeating this, we get all these posterior draws I showed you before. Now this normal distribution example, it's again one of these simple models. And already in this lecture, we go to a model where we don't have these analytical solutions, and we then go to numerical approximations. Discussing about the normal distribution specifically, it's not just to show that how this can be complicated even for simple model, but it's also that then this normal distribution it's used so much also during the course that it helps that you have some connection also between these different functions you use in R or Python and then these equations. And of course those who are interested, I again recommend looking at these equations more detail and doing some of these exercises related to this. We can also look at this in that way, that instead of drawing drawing posterior draw of mu, we can also kind of look at how it looks like that if we make a collection of these posterior densities. So this is now the illustration of kind of how visually we can think that we have this hill. We take slices of that hill in different locations, and then in which locations, when we do the sampling approach, it's in those locations which are distributed as the sigma, and we get these samples of conditional distributions, and then average of those is the marginal distribution for mu. So especially later we mostly do just the joint posterior draws from more complex models, at some point using Stan, but it's useful to visualize these kind of that what is this marginalization means if we think about these joint distributions and marginals. And so we can then compute this marginal approximation for the marginal density as mixture of normal distributions. And so remembering again that in computers we don't compute this normal distribution in infinite many locations, but in finite many locations. But we can get these dashed lines by computing the normal distribution, conditional normal distributions in fine grid, and in those same grid locations computing the averages to get the plot for the marginal density. And here's a comparison then, average and exact. I go also this through the corresponding the marginal for mu. In the book there is this kind of this also told that how this integral is solved, but since it's kind of brief, I give some additional hints how you can see how this integral goes. So first we have the same joint distribution as we had before in the form where I use the sufficient statistics. So this is just the joint distribution here. Now we do just a transformation that the blue parts of this equation is now denoted with A, and then in addition now the extended blue part is denoted by Z. So A was the one which is inside the square brackets, and Z is then everything inside parentheses except the minus sign. Now we can then write this integral in this way. So inside the exponential we just have minus Z. Before that there's Z exponented to something and integral over Z. And then because we made the transformation, eventually we get then also outside of the integral this A to minus n per 2. Now we recognize gamma integral. So what is in the integral? You notice that it depends now what is the exponent of x. So there's x to u minus 1, but in that place we have n minus 2 divided by 2, but since that part doesn't depend, so that's constant, n is constant here. It means that then result of this integral is constant, and if it's constant we can drop it from the proportional part. Which means that we are left only with the a part exponented to minus n per 2, and then we can rearrange this to get this equation, which has been named students' t-distribution. We see again the benefit of having the sufficient statistic formulated in a certain way, that we have there mean of the data y bar and the squared errors or squared terms s squared divided by n. This was first derived by William Gosset. He was working at Guinness Brewery in quality control. So when you make beer, the quality of the ingredients, or what grains you get and what malts you get, what hops you get, these vary. But most of the customers enjoy that the beer should taste every time the same. They want the same tasting beer. So Guinness had the problem that when they get the ingredients, how they can quickly find out how to make from these ingredients beer which tastes the same as before. And then it's possible then to make measurements, but you don't want to make many experiments. You want to make a lot of beer to be sold, so there were always small sample sizes. And then Gosset realized that then in small sample cases, the uncertainty, it was not normally distributed, but there were more variation. He did also simulation experiments, so that he had written numbers in pieces of paper, put them in a hat, and then draw a small sample of numbers, and did experiment that if I now compute average of these small sample of numbers, how they are distributed. And eventually then came up with this equation. At that time, Guinness did not give permission for Gosset to publish this result, because Guinness did not want other brewers to know how advanced statistical methods they were using for quality control. So it was clearly a competitive advantage for them that they were getting more the same quality all the time out. But they allowed him to publish this with the pseudonym student, and that's why then quite soon later, it was then named as the student's t-distribution. Okay, and so you can remember connection next time you drink Guinness. Later, William Gosset then also was actually the head brewer at the Guinness London Brewery. Okay, let's have 10-minute break. So, during the break, there was a question about where does this prior sigma to -2 comes from, and there's a couple different ways we can come to that. One is that if we go to thinking about conjugate priors, we did see that previously was discussed that in the case of conjugate priors, the prior has to have the same form as the posterior. We've seen the marginal posterior for sigma is inverse chi squared. And also last time it was discussion that in this case of conjugate priors, the parameters of the prior can be considered to be presenting also that kind of the how much prior information we have, or how many prior observations we have. In case of if we use inverse chi-squared distribution as prior, and if we make it so that we make the prior information go to corresponding 0 prior observations, this inverse chi-squared distribution goes to this. Other way this is justified is that we would be scale invariant in a way that in this case we don't care whether we've measured something in meters or millimeters, and the kind of the change in the sigma, it doesn't matter that if we had kind of the same change from going from 1 meter to 2 meters or going from 1000 millimeters to 2000 millimeters, and then it's scale invariant prior. This is discussed also in chapter 3. So we got now, I go back to these marginals. So we got this marginal for mu, and then we can also look at this this predictive distribution. Here we have already factorized this predictive distribution. We could also write joint distribution. So y tilde is future observation, but we could have also joint distribution future observation, mu, and sigma. We could have a joint distribution for them. These are all unknown for us. We have some uncertainty, but then we have factorized this so that we have the marginal posterior for mu and sigma given data. Oh yeah, there should be data here also. And then we had a conditional part, y tilde given mu and sigma. And then we integrate over mu and sigma if we are just interested what we would expect to see in the future given we have a normal model and we have observed y. We can do this also by simulation, draw from the joint distribution, and then we can draw one simulated predictive distribution, and also draw from that one simulated predictive distribution one possible future observation value, which is as a red dot there. And then we can get more and more draws. Each of these predictive distribution is normal distribution given some specific mu s and sigma s values, and from each of those we can then draw value y tilde s. I've added some jitter so that they are going to have different heights, but you could see that there's more of those in the middle, less on the edges, and we can compare to exact predictive distribution. We have also in this case analytic solution, and then we can start with what is the predictive distribution given known variance. So we can put there the normal distribution, so there's a normal for y tilde given mu and sigma squared, and normal for mu given the sufficient statistics, and then we integrate over mu, and the result is again normal distribution. It has this location y bar, and then the variances are combined. So in this predictive distribution, now we have one part of the uncertainty is this epistemic uncertainty coming that we don't know mu, and the other part is this Aleatoricson uncertainty. Even if we would know mu exactly, we have still the uncertainty described by sigma squared. And then we can recognize that this predictive distribution is up to scaling factor, same as would be just the posterior distribution for mu given certain sigma, and we already solved what was the marginal. If we marginalize now the sigma, it was the student t distribution, and so we can put that, just that additional scaling factor there. In the book, there's an example. Simon Newcomb's. They made these light of speed experiments. Time required for light to travel from his laboratory on the Potomac River to a mirror at the base of the Washington Monument and back. 7,422 meters, and here are the measurements. And then we can find the sufficient statistics, mean, and the square terms. We get the posterior of mu. We come back later in chapter 6 how we can then analyze whether normal distribution is good model for this. There seems to be a couple observations quite far away from the others, which is unlikely for normal distribution. In this case, we can also just look at what if we would remove these two suspicious ones. Of course, the better one would be to modify the model that it would explain also these strange cases, and we get but anyway, removing them, we get this kind of posterior. And then as a reminder that when we make the posterior inference, the posterior inference can be only as good as the data. And in this case, if we compare to modern estimate, it seems that the modern estimate is quite unlikely given normal model and Newcomb's measurements. But this is likely just because Newcomb had some kind of bias in his experiment, so there was something which was biasing the result all the time in the same direction, and then it doesn't help if you get more observations. There was someone wrote a paper overall in different kind of these physical constants that how during the 20th century the estimate has changed, and from each paper where there was a new estimate, there was always also some statistical uncertainty, and all the time it was that these statistical uncertainty estimates were too narrow compared to the next estimate. So it was also that all the time people making these physical experiments, they had also some constant bias in the measurement process, and it didn't help that they collect more and more data. But we come back also then to the kind of the model checking, and we come back to later also in the kind of discussions that how well we can do depending on the data. So I started the second half already mentioning the conjugate prior, and here's a bit more. So for this normal distribution having these two parameters, has to be this kind of factorized form, and then from that we could have this joint prior, which can be written as normal inverse chi squared prior. But now, if we both of these, if we make them less and less informative, wider and wider, so this conditional mu given sigma squared is a normal distribution. If we there make kappa 0 to go towards 0, then this normal distribution gets wider and wider and closer to uniform. And in inverse chi squared, if we make nu 0 smaller and smaller, inverse chi squared distribution goes closer and closer to this one. And you can look at the exercise 3.9 for deriving then this joint posterior, but I don't go through it here. The chapter 3 also mentions multinomial model for categorical data. It's extensions of binomial discussed last week, but you can read more in the book. Multivariate Gaussian, you can again read in the book, and then you will later also use multivariate Gaussian in some of the exercises, but in that form that you don't need to know these equations. The book mentions in the chapter 3 the conjugate prior, but then in appendix A there's a new recommended LKJ prior, and also Stan Manual has more about it, and if you happen to use it. And as a reminder, conjugate priors used to be more important before. They are still sometimes useful, but with Monte Carlo, Markov chain Monte Carlo, we can use non-conjugate priors, and it's better to use that kind of prior which is better describing our information. The LKJ prior has the benefit compared to conjugate prior that we can separately tell information about marginal variances and correlations. Okay. Rest of the lecture I will go through this bioassay example, which is used many times in your exercises, and then also some computational things. This data is from experiment where when there are chemicals and manufacturer wants to sell that chemical in Europe, they need to check whether it's hazardous, and if it's hazardous they need to find out how hazardous. One way to then measure this, how hazardous something is with rat studies using certain standardized breed of rats, and then finding out what concentration given orally would kill approximately half of the rats. Of course, it's not nice that we need to kill rats, and there are a lot of these kind of animal experiments have been replaced also recently with just growing cells, and also possible then to grow human cells and look at the behavior specifically for human cells and not just rats. But then also this example is in that way good, that with Bayesian modeling we can use less experiments, and later in decision theory part you will also learn how to design of experiment and optimize what would be the next measurement and least amount of measurements that we can learn certain, like, more accurately how hazardous this chemical is. So in this case there's 5 rats in each dosage group, and then there's grams per milliliter and then logarithm of that. It's quite common to work in these dosages in log scale, and you can also see here in a way that it's seems to be quite reasonable in that way, that if we look at the range. And for each batch of the animals, then observe that there was 0, 1, 3 and 5 deaths, and then the data is plotted there. We could already, just looking at this figure, think that okay, yes, it's hazardous, because when we are increasing the dosage, more rats are dying. We could just by eye already estimate approximately what would be the dosage that kills about half, but we can also then make a model for this and get more accurate uncertainty estimates. So we want to find out this lethal dose 50%, and this data is that old that it was 1984 EEC directive, which has 4 levels, and you can read more in chapter notes. So we can reduce the number of animals needed, easy to make sequential experiments, and if we would use something else than animals, Bayesian methods could be also then used to make hierarchical models, kind of calibrating these other models based on animal experiments. Again, just the dosage and number of deaths. It seems that it's almost linear increase. We could make a linear fit. But just making a linear fit is in that way a bit silly, that if we now extrapolate, we can't have negative number of deaths and not more deaths than what is the batch size. So we should have a model which is constrained so that it would fit only between 0 and 5 deaths. We can do it so that we can also think about just the proportion of deaths, which is now between 0 and 1, and then this proportion of deaths is what we observed, and then there's a slash theta. The theta is then what is this unknown expected number, or unknown expected proportion of deaths if we would repeat the experiment with certain dosage. So that's our unknown parameter. We can use the same binomial model we had last week, so that we have binomial model for each different dosage. So we have here 4 different dosages, and so we would have 4 different binomial models, and we know already then how we can find out separately uncertainty for these. But now we want to make some connection between these models. One way to make this connection is to use this logit transformation. So we can still use linear model, but just transform that linear model so that the transformed value is between 0 and 1. And so we have here alpha plus beta times x1. So beta is still telling that when the dosage x increases, then there's some change also in this linear model, but now this linear model is not directly for the proportion, but instead we have this transformation. And it seems that this is also now nicely fits to the data. So we have now the linear model, and we call often that this is linear model in latent space. And then we have the logistic regression, because we have this logistic transformation. And now there's also then transformation backwards, so that we can find out, based on this linear model, what is the value for theta I. There are alternative transformations, but this is commonly used, and for in this case works well. So here we have again just the one fit, but then these same observations could be explained by other fits, and these are now posterior draws. You can see there are more blue lines such that they go close to all of these red dots observations, but there are also some which go a bit further. But since the blue line is giving just the kind of the what would be the expected proportion of deaths, it's still possible that we see less than more than what we expected. There's always some randomness in these processes. So we can have these posterior draws, but we were now interested in LD50. So what is the dosage that kills about half? So we can look where do these blue lines cross probability or proportion half. So there's a gray dashed line at half, and then blue dots where these different fits crossed at half. And these blue dots would now then tell our uncertainty about LD50. We can also, from this equation, this inverse logic equation, we can solve that this crossing happens at the value minus alpha divided by beta. And then these blue dots are now, the x values are now then these posterior draws. And now the nice thing about the posterior draws is that it's easy to compute these further derived quantities. So if we had a posterior draws from alpha and beta, it's easy to compute other posterior draws which depend deterministically from alpha and beta. This would be again impossible to have we don't even have the analytic posterior for alpha and beta, but even if we would have, it's unlikely that we would have an analytic solution for their ratio, or the posterior of their ratio. And then we can plot histogram of these, and we can compute intervals 5 and 95, and we can check, is this accurate enough that we can now classify this in the certain hazardousness level. So the posterior distribution, we have the binomial model, we have the link function. So the likelihood is just from the binomial, familiar from last week. And then we just put in the place of theta these inverse logits and the linear part. And then in the next plots, I use just a uniform prior, and you have an exercise where you use some other prior, and book also discusses alternative prior. Now for the computation, what we can do when we don't have analytic solution. I have here equidensity contours like I had for the normal distribution, but there's also color. So more intense red is higher density, and then lighter colors and white lower densities. And then in computer, this has been done also by computing the density in many locations. Here we often plot these so that they are actually just interpolated. We don't need to compute them in many kind of that. We can compute them in a coarser grid and then interpolate, and here's the effect of the interpolation. So it's been actually computed in this grid. You can see now the squares, and now the value is the same in each kind of thing. The value is constant in each square, and the density was evaluated only in the middle of the square. But since this is smooth density, then it looks better if we just interpolate. And then it looks like that we would have been able to evaluate it in many locations. And based on these interpolations, also these equidensity contours are made. So this is one way now in this specific Vyasa example. When you make your exercise, you are also using now this grid evaluation, and it works in this low dimensional case. Here the density is evaluated even in coarser grid, just to give you even more kind of clear that how it would look like that if we evaluate only in the middle of some square, that we can use those also to compute. Here, so there was in the during the first part of the lecture, there was a question that what do we do when we don't know the normalization constant? Here, we don't need to know normalization constants also when we do these plottings. One possibility is also that we do self-normalization in that way that we now, so this 2D thing, the corresponding thing in 1D would be that we would evaluate density certain locations and make boxes for those. Even if these densities in middle of these bars would be unnormalized, we can now then compute that we want to say that summing these values have to sum to 1. So we count sum of these values and divide the unnormalized values by that sum, and then the new values will tell what is the probability that the posterior, the kind of the theta in posterior would be in this interval. So that's the self-normalization part. So this now shows everywhere we evaluated it. You can see that we have been evaluating it in many locations which have very small density, and after normalization they would have very small probability. This is the problem with the grid evaluation, that we often evaluate in, first we need to know big enough square where to evaluate, that we are certainly including all the interesting parts. But even then it's likely that then we are also evaluating somewhere which are not that interesting. And this gets worse in higher dimensions. I'll discuss about that later more. So density times cell area gives probability mass in each cell if we would have normalized densities. If we don't have normalized densities, we can do self-normalization. And then if we have normalized, this is showing now that there should be now showing also in the figure numbers at the top. So starting from the topmost and next to it, few of those locations 1, 2, and 3 should be marked. We have certain densities, and then we can take into account the cell area, we get probabilities, and then probabilities over each cell sums to 1 when we have these normalized. Then one way to going from this grid is to sample according to these grid cell probabilities. So in 1D, each part tells what is the probability that it would theta would be in this interval, and we just sample according to these probabilities. And it's just one draw could be then from here, any of these bars, and but of course most often we get from here, and then next often here, and so on. So here's 1 point sampled according to these grid cell probabilities. Here's more. We get more draws near where there's high density and less where there's a low density, and even more. Now several draws can be from the same grid cell, and now it starts to get kind of difficult to see anymore the shape. We can add for visualization a bit of jitter. It's not needed for computations, but for visualization. So I just added to the this alpha beta values of each draw bit of random noise so that they are not overlapping, and then we can see again better that we have more draws where there's a high density, less draws where there's less density, and if the density is small enough, we don't have any draws from there. And now these draws can be used to estimate expectations. For example, we wanted to know this LD50, and we can then compute the empirical estimate, empirical average given these alpha S and beta S posterior draws. It is also possible that instead of having this additional sampling part that we have these random draws, we could use this grid to evaluate functions directly. And then in that case we would have here now the index is t, just to make a difference to that S. It's quite similar equation, but now it is just that each alpha t, beta t value is weighted by that normalized probability of grid cell T. And then this grid integration is actually more often done without sampling, But then, because in the course we are going to higher dimensional examples where the grid evaluation does not work anymore, then we also use it already in this example, the sampling-based approach. There are also this in chapter 10 mentions few other of these kind of deterministic approaches. So in a sampling we had this random sampling from the distribution, but if we just use this grid, this is called deterministic approach, where we have determined, not randomly but deterministically, location of these draws. This is connected to quadratures also, so they are also, especially in 1D and in some lower dimensional cases, there are more clever ways that if we know something about the distribution, how we could put these points there, less points, in a clever way, that when we compute something like here, the second equation, that this capital T would be small and we would need to evaluate in small number of locations, but that approximation error would get small quickly with more draws. So with the deterministic approaches we usually get smaller error. We can place them more in a clever way. In the sampling we have a bit of additional variation from the sampling procedure, and we need a bit more of these draws. But when we go to higher dimensional examples, it just happens to be that in general case it's so much easier to use these random sampling approaches, and then these deterministic ones are good in special cases. The grid sampling gets computationally too expensive in high dimensions. I'll come back to that later also, but you can think of it already based on this slide, that now we have here two corners which are specifically empty, and if we add third dimension, there are more and more corners which are empty, and then it's difficult to visualize 4 and 5 and so on dimensions. But in high dimensions, most of the corners are empty and most of the grid points would be in low density areas. Okay, that was the last slide this time. So there was a question that how many of these posterior draws we need to get certain accuracy. And this is answered in more detail in chapter 10. But we can already see that if we look at this first equation and we want to know what is the mean of some observations. So we have observations from posterior distribution, and then we know that when we have more and more observations from something, that mean is going to be closer and closer distributed as normal distribution. So we can use that same normal distribution model we discussed during today, and we can get kind of what is the uncertainty about that mean. So that gives directly the kind of what is our Monte Carlo standard error then. In case of these kind of when we compute just the mean, it's quite easy, and then there are kind of, instead of if we are looking just the posterior mean, if we want to look at different quantiles, for example, when we are estimating some posterior interval, saying that with 95% probability LD50 is between this interval, we might sometimes also want to know how accurately we actually know where these endpoints are. And we can use the same kind of approach. There are a bit additional things we need to take into account, but there's a paper describing the details that we can compute these Monte Carlo standard errors for any quantities we can think of. And it's just kind of adding another level of statistical inference there, estimating that error. Other questions?